Hello, everyone. Thank you for being here today. My name is Dr. Pavlo Radiuk, and I'm excited to present our work on explainable artificial intelligence, transitioning DL model decision to user-understandable features in healthcare. This project is a collaboration with my colleagues, Professor Doctor of Science Oleksander Barmak, Professor Doctor of Science Eduard Manziuk, and Professor Doctor of Science Iurii Krak. Let's dive in. Deep learning has brought incredible advancements in medical AI, but there is a major challenge, the black box nature of these models. Healthcare professionals find it difficult to trust these systems when they can't fully understand how decisions are being made. This lack of transparency can undermine their trust and hinder the safe application of AI in critical areas like medical diagnosis. Our goal with explainable AI is to bridge this gap, making AI outputs more transparent and interpretable for clinicians, which is critical for trust and accountability in healthcare. The main purpose of our study is to enhance the interpretability of deep learning models by developing a scalable approach that translates AI decisions into features that healthcare professionals can understand. We extend an approach we previously developed, and this time we apply it to medical tasks like electrocardiogram, ECG, and magnetic resonance imaging, MRI analysis. We aim to make the DL model decision clearer, even when no corresponding machine learning model exists to compare with them. Our methodology revolves around two key matrices, A and B. Matrix A represents the features extracted from the deep learning model, and matrix B contains features that are understandable to healthcare professionals. Using singular value decomposition, we compute the pseudo-inverse of matrix A, which allows us to calculate the transition matrix T. This matrix transforms complex DL models' outputs into features that professionals can interpret. The basic approach begins with mapping feature vectors from both the DL and ML models onto a visual plane. Next, we apply singular value decomposition to calculate the pseudo-inverse of matrix A. Finally, using the transition matrix T, we transform the DL features into something that healthcare professionals can interpret, bridging the gap between complex model decisions and understandable medical features. In the scalable approach, an expert identifies the key features needed for classifying objects in the dataset. We assign numerical ranges to these features, allowing us to determine class inclusion. We then calculate feature values for each object, which are compiled into matrix B. This allows us to translate DL model results into interpretable data, even when no ML model is available. We applied this approach to two datasets, ECG signals and MRI scans. For ECG, we worked with triads of cardiac cycles, as shown in figures A and B, and for MRI scans, we analyzed segmented heart images, as shown in figure C. These experimental setups allowed us to evaluate how well our approach works for different types of medical data. For the ECG dataset, we focused on classifying premature ventricular contraction, or PVC. Cardiologists help us identify three critical features: the absence of the P peak, an expected and deferred QRS complex, and a complete compensatory pause. Using these features, we ensured that DL model's decisions were aligned with real-world medical insights. In the MRI dataset, we focused on heart conditions such as dilated cardiomyopathy, and hypertrophic cardiomyopathy. Key features included left and right ventricular volumes and myocardial wall thickness. These features provided cardiologists with interpretable insights into the state of the heart, which allowed us to better understand the DL model's classifications. To measure the reliability of our approach, we used Cohen's kappa coefficient, which evaluates how well the model's predictions aligned with expert annotations. For ECG, the agreement between expert and the model was almost perfect, with a kappa value of 0.98. For MRI, we saw a strong agreement with a kappa of 0.87. These results show that our approach effectively translates model predictions into understandable insights. Let's look at the results for the ECG dataset. Our DL model achieved a training accuracy of 99.95% and test accuracy of 99.13%. The kappa value, measuring agreement between the model and experts, was 0.98, showing nearly perfect agreement. Our key takeaway here is that the DL model's arrhythmia detection closely aligns with expert annotations, proving its reliability. For the MRI dataset, our model had a training accuracy of 97.4% and a test accuracy of 96.5%. The kappa value, again measuring agreement between model predictions and expert label data, was 0.87. These results highlight the model's effectiveness in classifying heart diseases and demonstrate its potential in real-world clinical applications. While the approach shows promise, there are some limitations, of course. One is feature selection bias, relying too heavily on expert-defined features that could reduce the model's ability to generalize. There is also the challenge of scaling this method to more complex data sets and maintaining consistent feature quantification across different experts. However, the scalability of the approach is promising, and further work is needed to enhance its adaptability to different datasets and clinical environments. In conclusion, our scalable approach significantly enhances the interpretability of deep learning models in healthcare. It translates complex AI decisions into features that are understandable to healthcare professionals. Despite the success, future works, of course, needs to focus on reducing feature selection bias and improving the model's adaptability across various medical datasets and domains. Thank you for your attention. We welcome any questions you may have. Please feel free to reach out to us via email if you have any further inquiries.